Hey, we're Mateusz,
Paul Nicholas,
and Martin Tamke from CITA, and we are involved in an exciting research project which uses Autodesk Forge. Here we aim to establish the foundation for research with machine learning on the Autodesk Forge platform. In architecture, we are increasingly able to incorporate real-world data into our design practices. But this means that our models get bigger, wider, and deeper. This challenges the infrastructure that underlies contemporary architectural profession. Architects and engineers need to find new models and methods to engage in these data-rich processes.
At CITA, we've been investigating and developing these methods within the ongoing Complex Modelling project, which is a blue sky project funded by the Danish government. Several of the sub-projects within Complex Modelling have explored machine learning as a way to better use data-rich environments. In the early exploratory stages of design, we've investigated the use of machine learning to cluster the large solution spaces that computational tools create, so that designers can focus on the most interesting solutions.
In more detailed stages of design development, to provide structural feedback in areas where traditional finite element calculation would fail.
and in informing fabrication by synthesizing data on material and its performance with the fabrication requirements.
The recurring problem on these projects has been the necessity to tailor machine learning and pre-processing to each project, the lack of existing tools, and the limits of desktop computation. This was the beginning for the Forge project.
Our collaboration with Autodesk was about testing how the Forge platform could help us to overcome these problems.
For this, we developed our own software based on the Design Automation API. We could indeed overcome some of the problems using Autodesk Forge.
We used the ongoing CITA project to bridge too far as a testbed and extended its scope. The project investigates digital fabrication and the use of robotic incremental sheet forming to rigidize very thin sheet metal and make strong, lightweight structures. The machine learning problem lies in the fabrication process. The benefits of using two robots is that we don't need molds and can customize the forming of each panel. But there is a drawback, which is that springback becomes a problem. Springback is the tendency of the material to return to its original shape. As we were making prototypes, we were able to observe that multiple factors appeared to play a role. The depth and angle of the forming, the proximity of the tooltip to the frame, irregularities within the material itself, and the calibration of the robot arm and the moment frame. We realized that it wasn't possible to model the high level of interaction between these factors using conventional mechanical models, so instead we looked to supervised machine learning.
The basis for the machine learning process was a supervised neural network. We trained this neural network based on the 3D scans of the panels compared with the measured deviation from the 3D models. The resulting data was encoded as a depth map, from which we gathered thousands of samples. Those samples were used to train the neural network the material behavior so that it is possible to predict and correct for springback. The amount of samples greatly influences the precision of the neural network predictions. Because we were working on local machines, we had to limit the number of samples we could process. Moving from the desktop into the cloud, we used Forge Design Automation API to develop a massively scalable solution. Our process consists now of 4 steps. Initial modeling process and fabrication. The discretization, that is translating the fabricated and the target geometries into a dataset done using a custom Forge application. Learning from the given samples using the TensorFlow framework. Model adjustment step performed. A flexible solution for this task was created, running AutoCAD Core in the cloud, coupled with the OWL library. This can scale up seamlessly with new problems given. The workflow consists of 3 .NET applications, easing the process of creation, setup, and using of a custom Forge application. App Command, which is the application running in the cloud, App Creator, which helps set up the application, and finally the App Client, which runs the application.
Using the cloud-based processes, we could move from extracting and pre-processing 4,000 samples in 20 minutes to 500,000 samples in the same time. A 100-fold increase. And if we would use even more computers in the cloud, the scalability is in principle limitless.
Our predictions had much greater accuracy, which meant that we could not only implement better corrective methods, but also explore a wider range of design options and geometries with more confidence.
Machine learning combined with cloud computing provides a powerful model to the architectural profession. A promising next step would be to move the machine learning itself into the Autodesk Forge cloud, where it could be widely distributed to other collaborators or users.
With the computational power of the cloud, fundamental research questions about the use of machine learning in architectural practice can be addressed, and new modes for creative engagement and design decision-making developed.